Welcome back, everyone, for another deep dive. This time, we're going to be looking at something that's always kind of blown my mind. Quantum tunneling. You know, there's tiny particles. Somehow they manage to slip through barriers
Yeah.
that, by all rights, they shouldn't be able to.
It really shows you just how different quantum mechanics is from like our everyday experience. It's wild.
It is. It is. And usually we kind of just accept that the particle that comes out on the other side is the same one that went in, right? But you brought up some really interesting questions about that, especially based on all the research we've been digging through. We've got research papers, some notes from a lecture you went to, and even that wild conversation we had with ChatGPT about it.
And what's fascinating is how they all kind of point to the same problem. Like, does this same particle idea even make sense if we think about one of the most basic laws of physics, the second law of thermodynamics, entropy and all that?
Okay, so before we go too deep down the rabbit hole, let's back up a bit. For our listeners who might not be familiar, can you give us a quick rundown of what quantum tunneling actually is?
Sure. Imagine you're trying to roll a ball up a hill. Now, in normal physics, if the ball doesn't have enough energy to reach the top, it just rolls back down, right? But in the quantum world, there's a chance that ball could just pop up on the other side of the hill as if it went straight through.
Yeah, that's definitely not how hills work where I come from. So how do particles pull off that magic trick?
Well, it all comes down to this crazy idea that matter can be both a wave and a particle at the same time. In quantum mechanics, we don't think of particles as tiny little balls. Instead, they're described by these things called wave functions, which are basically like maps of probabilities.
So it's not so much about where a particle is, but where it might be. Like it has a chance of being in different places.
Exactly, and that's the key to tunneling. The wave function doesn't just stop at a barrier, it kind of bleeds through it, meaning there's a small but real chance that you could find that particle on the other side.
Okay, so it's like the particles rolling some cosmic dice. Like, will I be here? Will I be there? Maybe I'll just zip right through this wall.
Uh-huh. Yeah, that's a great way to put it. And since there's that chance, well, sometimes the particle wins the game and pops up on the other side, even if it didn't seem to have enough energy to get there.
So scientists can't actually see this happening. They just see it vanish on one side and reappear on the other.
Yep, we can't actually watch the particle while it's tunneling. We only see the before and after.
Okay, so then how do they even know that tunneling happened?
We look at the particle's properties before and after, like its energy, its charge, its spin. If all those things are the same, we assume that tunneling must have taken place.
So it's like a magic trick.
Yeah.
But the scientists are trying to figure out the illusion by looking at the props before and after the disappearing act.
Exactly. But here's where it gets interesting, and this is where your question comes in. If it really is the same particle popping out on the other side, doesn't that kind of mess with our understanding of, entropy?
Ah, yes. Entropy, the universe's tendency to get messier over time. So how does tunneling fit into all of that?
Well, the second law of thermodynamics states that entropy in a closed system always increases. It's like if you leave a room alone, it'll naturally get more messy, not more tidy.
Okay, I see where you're going with this, but what does a messy room have to do with a particle going through a barrier?
Think of it this way. Each possible way that particles can be arranged in a system is like a different arrangement of mess in that room. And each of these arrangements is called a microstate.
Got it. So more microstates, more mess, more entropy.
You got it. Now, if a particle tunnels, and it's really the same particle before and after, the system's microstates haven't actually changed. It's like if you spent all day cleaning your room and then it instantly went back to being a mess.
No, that would be frustrating. And it doesn't sound very entropy friendly either.
Exactly, and that's the paradox. How can tunneling, something that happens all the time, maybe even be essential to the universe, potentially break this fundamental rule of physics?
All right, I'm officially hooked. But before we jump into potential solutions, we need to unpack something you mentioned earlier, this whole idea of the same particle. You seem to be hinting that maybe it's not so straightforward in the quantum world.
You're right. The research, particularly the stuff on quantum field theory, suggests that maybe thinking about a particle having a fixed, unchanging identity might not be the best way to look at it, especially when it comes to tunneling.
So are we saying goodbye to the same particle idea entirely?
Well, not necessarily, but maybe we need to rethink what same means in this context. Maybe it's not about tracking a single specific particle as it goes on its journey.
All right, now I'm really curious. What's the alternative then?
Well, think about it like this in the quantum world when we're dealing with particles that are fundamentally identical, like electrons or protons. It becomes impossible to tell them apart. It's like trying to tell apart identical twins.
So If two particles are truly indistinguishable, how can we even talk about one being the same as the other?
And that is the million-dollar question. And it's this indistinguishability that might hold the key to solving that whole entropy paradox with tunneling.
Okay, so we've laid out the mystery. We've questioned what we even mean by same particle. Where do we go from here?
I think we need to explore this idea that even if particles seem identical, they might be changing in subtle ways during tunneling. Changes that are just too small for us to detect right now.
Okay, so we're not tossing out the second law of thermodynamics just yet. We're saying there's more to the story, something we're just not seeing. All right, I am ready for some mind-blowing revelations.
Let's see if we can blow your mind then. So we've kind of established that saying it's the same particle after tunneling might be a bit too simple. The research we dug up really dives into this other possibility, that the particle actually changes in some way during tunneling, just in ways we can't quite measure yet.
Okay, so it's not like it's magically teleporting, totally unchanged. Something's happening during that trip through the barrier. But if these changes are so small that we can't even measure them, how do we even know they're there? Kind of feels like we're just guessing, doesn't it?
It might seem that way at first, but we have to remember this whole principle of entropy, right? The universe tends towards disorder. It's like baked into the fabric of reality. So the idea that tunneling, something so fundamental, just ignores that. It doesn't really sit right.
I see what you mean. It'd be like, I don't know, like saying a river can flow uphill.
Yeah.
Just wouldn't make sense given what we know about how things work.
Exactly. And that's what makes this idea so interesting. It brings quantum mechanics and, the bigger laws of physics together. Tunneling might not be an exception to entropy. It might even be part of it.
Okay, I'm with you on the whole entropy thing. But what kind of subtle changes are we talking about here?
Think about the wave function again, like a really complex tapestry of probabilities. Now, when it hits that barrier, it's not just passing through untouched, it's interacting with it. And that interaction, even if it's tiny, could be rearranging those probabilities in a way.
So it's not a smooth ride through the wall, more like a bumpy one that shakes things up a bit.
Yeah.
And those little rearrangements, those shifts in probability, those are what add to the entropy.
Exactly. It's like shuffling a deck of cards. If you shuffled them perfectly, ending up with the same order would be, astronomically unlikely. In the same way, the particle going through the barrier adds randomness. It makes it really, really unlikely that its wave function stays the exact same.
Yeah, okay, that makes sense. But this is a lot to wrap my head around.
Yeah.
We're basically saying that what we call the same particle might actually be different after tunneling, just in a way we can't quite grasp.
That's right. And that difference, even if it's tiny, could change how we understand the quantum world and how it fits into the bigger universe.
Wow, okay, I'm trying to grasp the scale of this. We're talking about rethinking what a particle even is.
Right.
Not just where it is, but its whole identity.
Exactly. And it's not just theoretical. This has practical consequences for how we measure things at the quantum level, how we understand energy, even future technologies.
Well, hold on. Technologies? What kind of technologies could be affected by something this, well, abstract?
Think about it. If we figure out how to detect these subtle shifts, we could build sensors that are crazy sensitive. Like, imagine sensors that could pick up tiny changes in biological systems that could be used to catch diseases super early, way before any symptoms even show up.
So we're talking about diagnosing diseases before they even happen. That's like a quantum crystal ball for your health.
It kind of is. And it goes beyond healthcare. Imagine materials that change based on these shifts, changing how we do computing or energy storage.
Okay, now that's getting my sci-fi senses tingling. But let's not get too far ahead of ourselves. We're still talking about a hypothesis here. Before we start building those quantum crystal balls, how do we even prove these changes are happening? What's the next step?
We need experiments that can actually detect these tiny changes in a particle's wave function. One way is to use something called quantum state tomography.
Quantum state tomography. That sounds really complicated.
It sounds complex, but the idea is actually pretty simple. It's like taking a detailed snapshot of the particle's wave function before and after it tunnels. Any little changes would show up in those snapshots.
So it's like a before and after photo shoot for particles. Instead of wrinkles or a bad haircut, we're looking for changes in probabilities.
Haha, yeah. Another way is to look at interference patterns. When particles tunnel through a barrier and then go through, say, a double slit experiment, they create these patterns of light and dark bands.
Oh yeah, the double slit experiment. I remember that from physics class. It's the one that shows how particles can act like waves, right?
That's the one. And the cool thing is, that pattern is super sensitive to the particle's wave function. So if tunneling causes those probability shifts, those changes could show up in the interference pattern.
Okay, I'm starting to see how those experiments could give us some clues. But even if we can prove those changes are happening, it still feels kind of abstract. Why should we care about all of this? What's the bigger picture?
Well, for one, it would change how we understand the universe. It means that even the empty space between particles isn't really empty. It's a field of probabilities,
Hmm.
always in motion. It suggests the universe is more connected than we thought.
So it's not just about the particle changing, it's about changing how we see reality itself. It's like, I don't know, realizing the pixels on your screen aren't just static dots, but are constantly changing to create the image.
That's a great way to put it. This shift in perspective, seeing how connected and dynamic the quantum world is, could change how we think about everything, from physics to philosophy to even ourselves.
Okay, I think my brain needs a break. We went from a question about tunneling to rethinking reality.
Haha, it is a lot to take in. But that's what makes these deep dives so cool. They push us to think beyond the surface, question what we think we know, and embrace the mysteries of the universe.
Well said. But before we get too philosophical, let's bring it back to those tech applications, early disease detection, those crazy new materials. Can you give us a sneak peek into how those might actually work?
Imagine a future where we have sensors that can pick up the tiniest changes in your cells. They could spot the first signs of disease way before you even feel sick.
So it's like an early warning system for your body,
Yeah.
running on quantum mechanics.
Exactly. And if we catch those changes early enough, we might be able to stop a disease before it even starts.
Wow, that's incredible. What about those new materials you mentioned?
Well, if we crack the code on controlling these probability shifts, we could make materials that do things we can't even imagine right now. Imagine materials that can change how well they conduct electricity, their strength, even their color, all just by tweaking those quantum probabilities.
Okay, now we're talking about some serious game changers. But hold on a sec. Wouldn't that need us to control the quantum world way better than we can now?
You're absolutely right. We're just starting to explore these possibilities. But the point is, by questioning this basic idea of the same particle, we've opened up a whole new world of scientific and technological possibilities.
It's amazing how one little question can lead to so much.
That's the beauty of science, right? Sometimes the biggest discoveries come from challenging what we think we know.
Okay, my head is spinning with all these possibilities.
Uh,
But let's take a step back, remind ourselves what this deep dive is really all about. You mentioned earlier that even though we can't measure those probability shifts yet, there's a good reason to think they're happening based on, well, the universe itself.
Right, it goes back to entropy. In your notes, you pointed out how evolution, like all the diversity and complexity of life, that's a prime example of how disorder or randomness keeps increasing.
So even if we can't see those tiny changes at the quantum level, the big picture from the Big Bang to life on Earth tells us they must be happening.
Exactly. The universe is the biggest experiment there is. And it's telling us that entropy is a driving force. So for tunneling, this really fundamental process, to somehow ignore that, it just seems, I don't know, impossible almost.
It's like imagine a library organizing itself, like all the books flying off the shelves and putting themselves in alphabetical order. Doesn't really make sense, does it?
Nope. And that's what's so cool about this hypothesis.
Yeah.
It's challenging, but it fits. It brings quantum mechanics in line with how we understand the rest of the universe.
Okay, so where do we go from here? What are the big takeaways for our listeners? Because I bet some of them are feeling a little lost in all this quantum weirdness.
Well, first off, I think this shows us that even simple questions can lead to some really profound answers. I mean, we started with, is it the same particle? And ended up talking about quantum mechanics, thermodynamics, even philosophy.
It's been a wild ride for sure. And I think it also shows us that science is never finished. We're always learning, changing our minds, and pushing the boundaries of what we know.
Yeah, and sometimes the biggest discoveries aren't about finding some new particle or force, They're about changing how we think about the universe at a really basic level.
Okay, so takeaway number one, always keep asking questions. Takeaway number two, the quantum world is way weirder than we thought. Anything else we should leave our listeners with before we wrap things up?
One more thing. Even though we haven't proven these probability shifts yet, the potential is huge. We've talked about medicine, materials, energy. I mean, it could change everything.
We're dealing with a what if, but a really big what if. All right, I think it's time for our final thought-provoking question, something to leave our listeners pondering. What do you have for us?
How about this? If these shifts are happening, if it's how the universe works at a deep level, what does that mean for the idea of identity? Not just for particles, but for everything.
Whoa, that's a deep one. Are we always changing, even if we don't notice? Is who we are just a bunch of shifting probabilities?
Those are questions philosophers have been wrestling with forever, but now quantum mechanics is adding a whole new layer to it. It makes you realize how much we still don't know about reality.
Well, I definitely need some time to think about that one. Thanks to all our amazing listeners for joining us on this deep dive into the quantum world. We want to hear what you think, so let us know your theories.
And until next time, keep exploring, keep those questions coming, and keep diving deep.